Let me remind you that we have two different flavors of a mass oscillating on a spring. We have the vertical case where it bobs up and down, and we have the horizontal case, which is simpler, where we will always assume a frictionless surface that the block or ball or whatever it is sliding across. Now, because of that frictionless surface, the weight force is always going to be balanced by the upward normal force of the surface. So if you look at problem 13, the one that we didn't turn in, we have a horizontal oscillation where it's going back and forth between 16 centimeters to the right of equilibrium to 16 centimeters to the left of equilibrium. Back and forth, back and forth. Now they ask you to draw a free body diagram when it's over here. It's at 12 centimeters to the right of equilibrium. Well, if I do that, I have weight down, that's 40 newtons. I have a normal by the table up, and I have a spring force. Now, if the equilibrium position is here, and the turnaround position is here, and I'm right there, is the force by the spring going to be to the right or to the left? To the left. Now, does it matter whether I assume that the spring is connected to the wall on this side or whether the spring is connected to the wall on that side?
Yes.
No. Regardless, either way, it's a restoring force. The force by the spring is a restoring force, meaning it's trying to push it back towards equilibrium. If I've got the spring anchored to this wall, then when I get over here, the spring is stretched and it's trying to pull it back towards equilibrium, and the force by the spring would be to the left. Well, if I anchored it over here, and if this is equilibrium, well then if it's over here, that spring is compressed and it's pushing, but it's still a force to the left. If I'm to the right of equilibrium, the force is going to be back towards equilibrium, namely to the left. And it's going to be equal to K delta S by Hooke's law. Now, anytime you draw a free body diagram, you get to use Newton's second law twice. Once in the vertical direction, once in the horizontal direction. I have no acceleration in the vertical direction, so that means that this normal force must balance this weight force. I now use Newton's second law in the horizontal direction. My only X force is this spring force, K delta S. And that has to equal the mass times the acceleration. And so I know that K is 100 newtons for each meter. I know that delta S, where I'm looking at it, is 12 centimeters, or 0.12 meters. And I know the mass is 4 kilograms. So I can solve for A. And I get 3 meters per second every second. Now, when I solve these problems, I always use energy. And in general, the energy in the system is going to be a combination of the kinetic energy of the block and the potential energy stored in the spring, be it stretched or compressed. Now, that's the general equation that always applies. There are special cases of that equation. At the turnaround points, at 16 centimeters to the right and 16 centimeters to the left, I have to stop to turn around. And at the turnaround point, my delta S is the biggest it's ever going to be. We give that a name, we call it the amplitude. Now some of you are thinking of delta S and A as two different variables. A is just a special value, the biggest value that delta S ever gets. Delta S is the variable that we're watching change as this thing goes back and forth. Delta S is how far you are away from equilibrium at any instant in time. And so we get this formula here because the V goes to 0 and the delta S goes to A. Now, in this problem, we are given the value of the spring constant and the amplitude. The first step in solving one of these problems is always to find the total energy. Usually that's part A of the problem. But if it's not part A of the problem on the exam, the first thing you should do before anything else is find the total energy. Okay? In this case, I know what K is and I know what the amplitude is, and so I can find the total energy from this special case of the equation at the turnaround. And I find 1.28 joules. Now, that energy stays the same no matter where this block is at the in the oscillation. I could have had another part to this problem where I could have asked you, when it's at this location of 12 centimeters, not 16 centimeters, but 12, how fast is it going? And you should be able to solve that problem. Which of these equations would you use to solve that problem? The first one. Because I'm not at turnaround and I'm not at equilibrium, I got to plug in 12 centimeters there and solve for V with my total energy being 1.28. I could also ask you, if this block is going at 3 meters per second, how far is it from equilibrium? In that case, you would plug in 3 meters per second here, 1.28 joules there, and you would solve for how far it is from equilibrium. And because this is a square, you would get two answers. You'd get a positive answer and a negative answer. And that's because it would be going that fast, whether it was to the left of equilibrium by that much or to the right of equilibrium by that much. Either way. Okay? So here's my promise to you. On the midterm, there'll be at least two of these problems, and I can dress it up any way I like. But it will be a horizontal oscillation with a frictionless table. But I can give you the amplitude and ask you for the fastest speed. I can give you the fastest speed and ask you how fast will it be going when it's 2 centimeters away from equilibrium. Any of these variations. Okay? Check that your neighbor's okay with that. Do a buddy check. Okay, other questions? Last day we talked about this Tacoma Narrows bridge disaster. Did I have time to explain what caused it?
No.
Okay. The classical explanation has been given for years and years, and was the accepted explanation when I was in graduate school, was vortex streets. If I look at a cross-section of the bridge, as the air went past the bridge, it formed an eddy behind the bridge, just like water going down a river behind a big rock like house rock will form an eddy. And that eddy is going to tug on the bridge. because it has low pressure and it tugs towards the eddy. Eventually, that eddy breaks free and goes downstream, and another eddy forms. So if we could color the air with some blue powder, what we would see is a whole bunch of these little eddies in what's called a vortex streak. They've all torn off, and then another one's formed, and then they tear off, and another one's formed. And the belief was that these tearing offs were happening at just the frequency at which this bridge wanted to oscillate. And that's what caused the resonance. Well, they later did a very sophisticated computer modeling of this situation and found that this would have given a different frequency than what was witnessed in the video. And so they have since come up with a different explanation called aeroelastic flutter. And this has more to do with the this bridge had some solid barriers along the side to protect people, and those barriers caught the wind, and so as the barrier caught the wind, it swung it to one side, and then it would swing back and then catch the wind again, and this thing was a feedback that happened at the right frequency at which this bridge wanted to oscillate. This is from the Intertube, so it has to be true. A contributing factor was its solid sides not allowing wind to pass through the bridge's deck. Thus its design allowed the bridge to catch the wind and sway, which ultimately took it down. Its failure also boosted research in the field of bridge aerodynamics, aeroelastics, fields which have influenced the design of all the world's great long-span bridges since 1940. So this was a learning experience, a painful one, in which we learned how to build bridges. Okay. Yes?
What was the wind speed when that happened?
42 miles an hour is all. And that's part of the surprising thing, is that you would have expected that this was some superstorm that they weren't anticipating. It was just a blustery day. Just the right wind speed in which to make it the right frequency.
Have you read anything about the harmonics and the cables that also?
I haven't. That's an interesting thing. We're going to get to harmonics, so let's not confuse the people around you until we get to the harmonics. But bring that back up when we get there, if you would. Okay, new topic. Ha! You people in the back, did you smell my bad breath? They did, but you did not. But both the people in the front and the people in the back had their eardrums assaulted. That was a pulse, a sound pulse. And a pulse is a disturbance that travels from one place to another. And it carries with it energy and momentum. That's what allowed it to push your eardrum in and pull it back out. But the important thing is about a pulse, the important thing is the medium that carries the pulse does not move very far from equilibrium. In other words, my bad breath that started the pulse didn't get past this front row. It didn't get to the other side. In that sense, it's very much like gossip. Okay? I never told you people back there that Pat was cheating on his girlfriend, did I? No, I never did. But I did tell Chat, and Chat told him, and he told him, and he told her, and she told him. That's the way gossip travels from one side of a city to another side, and he wasn't cheating on his girlfriend. I was making that up. I'm sorry, Pat, I apologize. Besmirch your good name. So, what happens is that every neighbor passes the information, or the disturbance in this case, to their neighbor. And the disturbance travels across town. Now, it turns out that there are two different flavors of pulse. Now you say, oh man, that's a lot to learn, but put it in context. If this were an anatomy class, how many bones would you be learning? Yeah? How many muscles would you be learning? Okay, two flavors. You can handle it. Okay? The first flavor is called longitudinal. And in this flavor, the medium that's carrying the pulse moves parallel to the direction of propagation of the pulse. Let me give you an example. I have this slinky that's supported by a piece of fishing wire. And if I think of this slinky, I mean it's one continuous piece of plastic, but if I think of it as parts, pieces, let's think of each hanging down part here as a separate piece. And the pieces are connected to each other, are communicating with each other through this spiral of plastic. Now if I pull back on one of these neighbors and let go, you see that a pulse propagates from your left to your right. Now I've identified one of the neighbors with a green string. Watch just the green string. Watch how the green neighbor propagates as this thing goes past. Okay? He moves away from equilibrium, back and forth, not very far, but he moves parallel to the motion at which the pulse is traveling, namely left and right. I have a computer version. Each of those dots represents a neighbor, a particle, if you will, of the medium that carries the pulse. Now, the arrows form or identify the equilibrium value locations, where they want to be, home, if you will. Now, as we create the disturbance, they're going to move away from home. When they get the furthest they're ever going to get away from home, they'll turn blue. So this is what it looks like as a pulse goes from left to right. That part of the disturbance that's furthest from equilibrium moves across the room. But each individual particle never gets very far from home. They don't get very far from their equilibrium position. Now there's also a perpendicular flavor. And as you might expect, in this case, the particles that carry the pulse move away from equilibrium perpendicular to the pulse. I have here what's called a Bell Labs wave machine. These things were made in the dark ages by Bell Laboratories. There's 2 of them in every physics department in the world, unless they've broken theirs. What it's made up of is a bunch of metal rods. And these metal rods would be independent of each other so that I could lift one without the others knowing it, except that they've each got a collar right in the middle. And there's a rigid wire that connects all the collars together, so that when I lift one of these rods, it twists the wire, which twists the collar, which pulls up the neighbor. And so by lifting one, I lift its neighbor. And you see that that disturbance just keeps on going, much like gossip across the town. Okay? But if I look at just one of these bars, just look at this one right here. Just try to focus your attention on that one. As the wave goes this way, left to right, it just goes up and down, perpendicular to the motion of the wave. And hence we call it transverse. Again, a computer version of that would look like this. Again, blue indicates the furthest it's ever going to get away from equilibrium. Okay? Now I have another version of that. This is a little bit more fun. I thought this was going to make me really, really rich. Didn't turn out. This is a metal chip from a milling machine. Any of you that have used a milling machine know that you get little chips. They're essentially the scrap metal that comes off of what you're working on. Well, the fellow that's running our shop came to my office all excited. He had spent most of the night being very, very careful to make this chip as long as he could make it. And this is as long as he could make it. And I was excited to see it because I could send transverse pulses down it. And the pulses just keep on going. Oops. Keep on going. Now, it used to work better, but I've stepped on it in places and put kinks in it. Now, I thought this was going to make me rich because I was going to have him stay up every night and make lots of them, and we were going to sell them to all the physics teachers in the world. It turns out there's not that many physics teachers, and they're all dirt poor. So there was no money in it. But we'll ask you some questions now with your clicker. What kind of pulse is sound? Is it transverse or longitudinal? Okay, last call. No. Was that you? Okay. Longitudinal is the correct answer. In order for a transverse pulse, I have to be able to lift my neighbor perpendicular to the motion of the pulse. In other words, I have to be tied to my neighbor tightly enough that when I'm lifted up, I can lift up my neighbor. Now, if you think about sound as it moves across the room in an ideal gas, you've all had enough high school chemistry or earth science to know that we model an ideal gas as a bunch of billiard balls, tiny, tiny billiard balls that don't interact with each other except through collisions. They're not putting forces on each other. We assume that they don't even know the neighbors are around until they bump into one. So when I go, ha! I'm sending a bunch of billiard balls this way that are bumping into a bunch of billiard balls that are bumping into a bunch of billiard balls, and so forth as they go across the room. Now, because these billiard balls aren't tied together, I can't possibly send a transverse pulse through the air. Okay? A transverse pulse would require this billiard ball to reach over and lift up its neighbor billiard ball. And they don't even know they're next to each other. Now, the same thing is true for any fluid. You remember in 205 we defined a fluid as anything that conformed to the shape of its container. That it be a liquid, or a gas, or a cap. Okay? And those were the three types of fluids. So what we find is that you cannot send a transverse pulse in a fluid like a liquid or a gas. Now that's why when a submarine wants to talk to home base, they have to come up high enough in the water to get their antenna out of the water. Because that radio wave is transverse. And it's going to move the electrons in the antenna perpendicular to the motion of the wave. Now, when that submarine is submerged, you can send a longitudinal pulse, a sound pulse, in the form of a ping. And that's what they do when they're trying to find a submarine by pinging it. They look for reflections, but those are sound pulses, longitudinal pulses. Now, when I graduated with my undergraduate degree, before I went off to MIT, I got a job at a research organization just for the summer. And I was working with a man named Harvey Fletcher, and he came from a very, very impressive family. Harvey's father was Harvey Fletcher Sr. Harvey Fletcher Sr. was the father of stereo. He was also the grad student who did the Nobel Prize winning experiment with the, Millikan oil drop experiment. He was the grad student that did that experiment. Harvey's brother, Peter Fletcher, was the director of NASA when we landed on the moon. And when the Challenger blew up, Peter was brought back out of retirement to clean things up. So I was working with Harvey, who was the less known brother in the family. And I went to Harvey one day very upset. I said, do you know that just down the hall they're working on sending transverse waves to submarines? He said, yeah. But transverse waves can't go through a liquid. Yeah, I know. Well, why are they working on that? Because they got a $4 million grant. But they can't do that. Greg, I know that. You know that. The Navy doesn't know that. It just blew my mind. Oh, man. I was very disappointed. Okay. That's not going to be on the exam. Okay. Now, another question with your clicker. You start a transverse wave going down a spring. Can I send a second transverse wave in such a way that it will catch up with the first one? Can I do something special to make that second pulse go faster and catch up with the first one? Yes or no? On the surface, you can create okay. Oh, the answer is no, according to our survey. Well, let's talk about that. The pulse speed is defined as, just very simply, how fast you would have to run alongside this spring to catch up with the pulse, to keep up with the pulse. Now, it turns out that that pulse speed depends on only two things when you're dealing with a transverse pulse. It depends on the restoring force, how hard we're pulling things back towards equilibrium. And the second thing is how hard it is to get them back to equilibrium, how massive they are. Now, if you're talking about a football player, you can talk about the mass of that football player. It's a unit, okay? Now, if you have something like a rope or a spring, talking about the mass of the whole spring doesn't really give you the information you need. Because I could have a spring that was a certain type of spring. If I had a mile of it, it would have half the mass as if I had 2 miles of it. Both springs would act the same, so the total mass is not going to give me what I need. What matters is the mass density. How much mass there is in 1 unit of length, typically a meter of length. And we can go through some fancy mathematics to derive this. I don't want to take us there. The final answer is that the velocity of the pulse depends on the tension in the spring or string or rope and the mass density of the spring or string or rope in this form here. Now this will be on the front page of your exam. It'll be in this form: tension over mass density, where mass density is mass over L. Now let's go back to that question that we asked. The mass density is fixed at the factory. Once a spring is created or a rope is created, it has a certain mass per unit length. Can't change that. And so the only way I can change the speed is to change the tension. So if someone were to pull on the other end of that spring, and I sent a pulse down here, it would go faster. The harder you pull on that spring, the faster the pulse is going to travel. But if I send one pulse down the spring, and then I try to speed up the second pulse by increasing the tension, both pulses are on the same spring. When I increase the tension, I speed up both pulses. They'll both be going, again, just as fast, and one started out behind the other. So the answer is it will never catch up. It will never catch up. See if your neighbor followed that, please. Do a buddy check.
What about
Well, unless it's a short.
I do wave pools. Wave pools.
Wave pools. I'm not sure what you're talking about. A wave pool.
Like a water park?
Oh, yes. That has to do with setting up standing waves, and we're going to get to that next week. Good point. I have been to one of those a long time ago. Okay. For longitudinal pulses, we're going to deal mainly with the most common type, namely sound. When I go, ha! That pulse propagates across the room. What determines how quickly it gets from this side of the room to that side of the room? What should matter? What should determine how quickly it moves?
The density of
The density of the air? Okay. So let me write this down. Density. What else?
any attractive forces in the fluid that you're...
Okay, we're going to assume that it's going through air and that the air is an ideal gas, so we're going to take that simplifying limit, but you're right. Other, raise your hand please, because I'm deaf. Temperature. Temperature. What else?
The force exerted by your voice, the initial force exerted by your voice,
The forces of...
the initial force.
Oh, the initial force with which you... Ha! Also the initial conditions. Initial conditions.
That would affect how far it goes, but not the speed.
Okay, we'll come back to that, Pat.
Other longitudinal forces.
Other longitudinal forces?
Like pulses. Like if you shouted, he shouted.
Oh, whether there's two going on at once, okay.
Not like reflective, like a wall.
Whether it reflects off. Okay, let's just take the simple case where there's one pulse and it's traveling in a straight line across the room.
The amount of particles, I guess.
The number of particles in the room?
Yeah.
Okay, that would be the density of how tightly they're packed.
Sorry, I missed that part.
Okay. Have you ever breathed in helium and then you talk like Mickey Mouse? That is because sound travels at a different speed through helium than it does through air, which is mostly nitrogen. And the difference is that helium is lighter. And so it turns out that the mass of the particle matters. It turns out what we find is that sound travels across the room as fast as the particles can travel. Okay? In order for this gossip to get across town, I got to take it to my neighbor, she's got to take it to her neighbor, and it has everything to do with how fast we can run and get to our neighbor. Now, it does not depend on density. I thought it should, but it doesn't. Let me see if I can explain why. Suppose we have a relay race. There's the start, there's the finish, and this relay race is between two relay teams, Bozeman and Belgrade. Bozeman has a large track team, and so they've got a lot of runners. And they just run and hand off the baton. Belgrade, not so many runners. Okay? But if we make the assumption that all the runners on both teams have the same average speed, this race is going to be a tie. Because no matter who's running, they're running at the same rate. And by the time this runner passes off the baton to the second runner, this runner has already passed that baton and already is passing that baton. And then this one goes and passes the baton, but in that same time, they've got the baton here, and they cross the finish line together. There will be more collisions, more passings of the baton with higher density, but the disturbance, the sound, doesn't get to the end of the row any faster than you can travel. Okay? And so what it depends on is how quickly the particles move. And we find that that's dependent on the temperature and the mass. Now, in air, mostly nitrogen, sound travels at 343 meters per second at room temperature, which is about 20 degrees Celsius. And we find that as the room heats up, it goes a little faster. 0.6 meters per second for each 1 degree Celsius that we heat up the room. And if we cool down the room, it goes a little slower. Now, the formula that we'll never use and will not be on the front page of the exam is this value here, this formula here, where this is the temperature in Kelvin, the absolute temperature in Kelvin. This is the mass of the particle in kilograms, and this K value here is not, I repeat, not the spring constant. This is Boltzmann's constant. It's a number that you're not going to have to use, so I'm not going to belabor you with it. Okay? Now, because sound travels faster in warm air, we have a phenomena that we call refraction, or the bending of sound. Now, this explains some things that happened to you when you were in 6th grade. You remember you were out on the blacktop, and it was a hot day. And the air was really hot down here by the black surface of the blacktop. It was cooler up above. Now, because these waves propagate as wave fronts, the wavefront down here in the warm air was traveling faster than the wavefront up there in the cool air. It's like pushing a lawnmower where one wheel goes fast and one wheel goes slow. You're gonna turn. Now you remember that day when you saw your friends, you thought they were your friends, on the other side of the blacktop. And you shouted, "Hey guys, come play with me!" And they pretended like you didn't exist. Did that happen to you? No, it didn't happen to me either. They never heard you. It wasn't that they don't like you, they never heard you.
And they don't like you.
On the other hand, when you're hunting in the winter, when there's snow on the ground, the sound bends the other way. And every little whisper travels back down to the elk, and they hear you in both. Okay? Does that explain things? Okay, let's talk about earthquakes with our remaining time. It turns out that earthquakes have both a compressional or longitudinal component called the P wave, and it also has a transverse or shear component, sometimes called the secondary wave. And both of these propagate out from the epicenter. Now, you can tell that it was the shear portion of the wave that caused that destruction there. Now, you've all heard of this standard model of the center of the Earth, that there's a region in there that's fluid. And the question always arises, well, how do you know? You have some magic digger machine that goes down deeper and deeper and superheroes go down? And no. What they do is they look at seismographs around the world whenever we have a major earthquake. And remember, a transverse wave cannot go through a fluid, a liquid or a gas. And so what they see is that there's a shadow on the other side of the Earth where they get the longitudinal part of the earthquake, but not the transverse part of the earthquake. And that's what leads them to believe that there must be some portion of the center of the Earth that is liquid. Okay, we've run out of time, folks. I'll post chapter 14 at the E2L site. See you on Friday.